I'm B. Maria Janis and I'm here to make a presentation on the topic thermodynamic equilibrium, reversible process, irreversible process, quasi-static state and a numerical as an example. So, first let's look into the contents. Thermodynamic equilibrium, and under thermodynamic equilibrium we have chemical equilibrium, mechanical equilibrium and thermal equilibrium, reversible process, irreversible process and quasi-static state. So let's understand all of these topics in detail with an example for each. Thermodynamic equilibrium. So what is thermodynamic equilibrium? It is a system in equilibrium where there is no change in macroscopic properties like temperature, pressure, etc. with respect to time. There are no gradients and there is no unbalanced driving force acting between the system or within the system and the surroundings. So hence, the system has no tendency to change its state. A system is said to be in thermodynamic equilibrium when it satisfies the three conditions. The three conditions are as follows. First, thermal equilibrium. Second, mechanical equilibrium. And third, chemical equilibrium. So when all these three conditions are satisfied, we can conclude or tell that a system is in thermodynamic equilibrium. Now let's look into the conditions for thermodynamic equilibrium for a closed system. So in a closed system, the temperature of the system is equal to the temperature of the surroundings, pressure of the system is equal to pressure of the surroundings, and chemical potential mu is equal to 0. Let's consider an example. A bottle of water is kept at room temperature. Here, the bottle of water is the system and the surrounding temperature or the room temperature is considered the surrounding. So, when this bottle is placed at room temperature, the temperature of the water inside the bottle and the surrounding temperature is equal. This satisfies the thermal equilibrium condition. Second, the pressure inside the bottle is equal to the atmospheric pressure. This satisfies the mechanical equilibrium condition. And lastly, there are no chemical reactions taking place and the composition of water is uniform throughout. This satisfies the chemical equilibrium condition. So, because or since all of these conditions are satisfied, we can conclude that the bottle of water at room temperature is in thermodynamic equilibrium. Now, let's understand what is chemical equilibrium. So, chemical equilibrium is a state where the rate of forward reaction is equal to the rate of backward reaction and the concentration of reactants and products are constant with respect to time. It is a reversible process. So, there are also conditions for chemical equilibrium. First is closed system. Why do we require a closed system? A closed system is necessary to avoid or prevent the entry or exit of any matter. Second, equal forward and reverse reaction rates. So, when the forward reaction and the reverse reaction is equal, then only the chemical equilibrium condition can be satisfied. So hence, the forward and the backward reaction rates must be equal. Constant temperature and pressure. So the temperature and pressure must remain constant to satisfy this condition. Even a slight change in temperature or pressure does not allow the system to attain equilibrium. And the last one is constant macroscopic properties. Once the equilibrium is attained, the macroscopic properties like temperature, pressure, composition, color, etc. of the reactants and as well as the products become constant and does not or should not vary with respect to time. Let's understand this with an example. So I have taken a reversible reaction between hydrogen and iodine gas to form hydrogen iodide. Here, the reaction is as follows. H2 in gaseous state, which is hydrogen, plus I2, which is iodine in gaseous state, and when both of these combine, we get 2Hi in gaseous state, which is hydrogen iodide. Here, the rate of forward reaction is equal to the rate of backward reaction, and hence the system is in chemical equilibrium. Now, let's consider this graph. This is a concentration versus time graph. The rate of forward reactance is given by this orange line, and the rate of backward reactance is given by this blue line. And when both of them satisfy the conditions, they attain this equilibrium called as the chemical equilibrium. Now let's look into what is mechanical equilibrium. Mechanical equilibrium is a thermodynamic state where the system has no unbalanced forces acting on it. The pressure inside is said to be uniform throughout the system, and this pressure remains constant with respect to time. Like the other two, we also have conditions to satisfy the mechanical equilibrium. First, there are no unbalanced forces acting between the system or within the system and the surrounding. Second, uniform pressure. The pressure inside is uniform throughout or is the same at every point within the system. Third, constant pressure. This pressure inside does not change or vary with respect to time. No bulk motion. There is no bulk movement of the system's components due to pressure difference. Here, I've taken piston cylinder system as an example. A gas in a cylinder with a movable piston is in mechanical equilibrium. Here, the pressure of the gas inside the system is equal to the external pressure on the piston, and any unbalanced force will cause the piston to move. This movement of the piston does not allow the system to attain mechanical equilibrium. Now, the last one, thermal equilibrium. Thermal equilibrium is a state where the two systems which are in contact with each other have reached the same temperature, and once they reach the same temperature, there is no flow of heat between them. This thermal equilibrium is a concept which follows the zeroth law of thermodynamics. The zeroth law of thermodynamics states that if system A and B are in thermal equilibrium with C, then A and B are also in thermal equilibrium with C. The key conditions are as follows. Same temperature. For both the objects in thermal equilibrium, the temperature should be the same. Second, no net heat transfer. Since both the objects have the same temperature, there should be no flow of heat between the object. This heat transfer will stop once the system attains equilibrium. Third, thermal contact. The objects must be in thermal contact with each other to allow transfer of heat until the equilibrium is achieved. This transfer of heat can be direct, which is through conduction, or indirect, which is through convection or radiation. Let's take an example of ice and water. So, let's take a glass filled with water and place ice cubes inside them and leave it to rest for some time. After some time, we can notice that the ice has completely melted into water. This is because there's transfer of heat taking place between the ice cube and the water, and when the equilibrium is attained, the ice has completely melted into water. And this satisfies the thermal equilibrium condition. Now, next we have reversible process. So, let's understand what is reversible process. A process is said to be a reversible process in which the system and the surrounding can be restored back to their original states. In this process, the external pressure is always small and close to the internal pressure, allowing the process to be reversed by the slightest change in external pressure. So when there is slight change in the external pressure, but both the internal pressure and the external pressure are close to each other, the process can be reversed. Conditions for reversible process: there should be no driving force. The driving force should be entirely small. There is no friction. It is a very slow process and takes lot of time. So, an example is ideal compression and expansion of a gas in a cylinder with a frictionless piston. So, this graph shows the reversible and irreversible process. This is a reversible process because the system and the surrounding can be reversed back to their original state, and this is an irreversible process. Here it cannot be restored back. And this is a graph. Here P1 is pressure 1, P2 is pressure 2, and this is volume 1 and volume 2. This is the area of work done in reversible process. So, next is irreversible process. Irreversible process is a process in which the system and the surroundings cannot be restored back to their original states. All the processes occurring in nature are irreversible process, and hence their path cannot be defined. And what are the causes of irreversibility? First one is friction. It causes irreversibility in the process as the work done is not equal to the rise in kinetic or potential energy of the system. Second, we have free expansion. This free expansion refers to the unresisted type of expansion, such as the expansion of a volume. During this expansion, the work done is zero, and there is no possible way to restore the initial state of this expansion. Third, heat transfer through a finite temperature difference. Heat transfer occurs only when there is temperature difference between the two bodies which are undergoing heat transfer. So hence the temperature should be finite for heat to be transferred. Fourth, non-equilibrium during the process. Irreversibilities are introduced when there is no thermodynamic equilibrium during the process, or the thermodynamic equilibrium condition is not satisfied when a process is taking place. Non-equilibrium may be due to mechanical, chemical, thermal, or electrical inequilibrium. So, an example to understand irreversible process is free expansion of gas. Consider we have a wall in which two gases are separated by a wall. So both of the gases are have different properties, and once the wall is removed, the both gases get to combine with each other, and get to combine with each other. And here the gases which are combined cannot be separated back to their original forms. This is an example of irreversible process. Then we have quasi-static state. When a process is in such a way that the system will be remained infinitely close with equilibrium state at each time, such a process will be termed as quasi-static state or quasi-equilibrium process. Or in simple words, we can also tell that all the intermediate points passes through the equilibrium. During the intermediate state, the system and the surrounding are in equilibrium. The process carried out is a very slow process and it is a reversible process. But not all reversible processes are quasi-static states. The example here, slow heating of water. Let us take a container of water. Let us take water in a container and heat it. The bath's temperature is increased infinitely. Here, the bath is the container which we have taken, and as the heat is transferred, the temperature of the container also increases slowly from its initial temperature to a final or a desired temperature. This allows the water to remain at thermal equilibrium with the container at each step. So as we place the container on a stove, as the heat passes through the container, the water starts heating up very slowly, and at each point there is different temperature in the water. This is an example of quasi-static state. Now, this is a numerical to understand the processes in a very detailed manner or a simple manner. A horizontal piston or cylinder arrangement is placed in a constant temperature bath. The piston slides in the cylinder with negligible friction and an external force holds it in place against an initial gas pressure of 14 bar. The initial gas volume is 0.03 meter cube. The external force on the piston is reduced gradually and the gas expands isothermally as its volume doubles. If the volume of gas is related to its pressure so that the product PV is constant, what is the work done by the gas in moving the external force? How much work would be done if the external force were suddenly reduced to half of its initial value instead of being gradually reduced? So, in this example, we have a gas in a horizontal piston or cylinder which is initially at a pressure P1 which is 14 bar and an initial volume V1 of 0.03 meter cube. So when the piston is allowed to expand till the volume doubles, we get a new volume or V2 which is 0.06 meter cube. We have two cases. First, the external force is gradually reduced so that the process is reversible and the PV is constant. Second, the external force is suddenly reduced to half of its initial value and the gas expands irreversibly to the same state. We have to find the work done by the gas in each of both of these cases. So, first, let's convert the constants to SI units, and 1 bar is equal to 10 power 5 pascals. And here, volume 1 is 0.03 meter cube and volume 2 is 0.06 meter cube. So first, for reversible expansion, PV is equal to constant or P is equal to K by V. Work done in reversible process is given by integral of limit V1 to V2 P dV, which is equal to minus K integral V1 V2 dV by V. Here, since K is a constant, minus K ln V2 by V1. So let's solve this equation by using this formula. we have V1, we have V2, and we have K. K is equal to PV. So pressure 1 into volume 1. Pressure 1 is given as 14 bars. So in pascals, we have 14 into 10 power 5 into volume 1 is 0.03. So the value of K is 42,000 joules. And by putting or substituting K in this equation, we get minus K ln V2 by V1, which is equal to minus 42,000 ln 0.06 by 0.03, which is minus 42,000 in ln 2. So we have the value of W, which is minus 29.112 joules. And now let's come into to find the final pressure P2, we have K by volume 2. So K is 42,000 by volume 2 is 0.06. So we have 7 into 10 power 5 pascals, which is the pressure of P2 or the final pressure. Now let's look into the second case, which is irreversible expansion. Here, after the sudden drop, the external pressure is equal to half of its initial pressure. So, P external is equal to half of P1. So, P external is 7 into 10 power 5 pascals. When the expansion, for sudden expansion against the constant external pressure, the work done by the gas is given by W irreversible is equal to P external into delta V. P external here is 7 into 10 power 5 pascals and delta V is 0.06 minus 0.03, which is the difference of volume 2 and volume 1, which is 0.03. So W is equal to 21,000 joules. This process is clearly irreversible, and when we have a comparison with the reversible process, we have 21,000 by 29.112, which is 0.721, or the efficiency is 72.1%. Thank you.